work with Diane Tosushi from Bordeaux University. And yeah, let me start by giving you the plan of the talk. So first I'll say a little bit of motivation. Where does that come from? Then I'll give the two main statements of the talk. And this is in part 2. Part 3 and 4, I will sketch the construction of two functors, which turn out to be quasi-inverse functors for the equivalence of categories, which is the main statement. So they're called Weil restriction, which is the usual one, and Weil extension, which is a new functor. And I'll finish with some speculations related to the original motivation, which is right now. So let me present two motivations. One kind of far-off motivation comes from early work that we had with Diano in trying to understand the models of mu-pn, which is, oh, maybe there's this appearing. So I have some pictures appearing on the right, which I cannot take away. Maybe it doesn't matter so much. Okay. Yeah, okay. Let me just also point out that there are numbers to the slides, 1, 2, 3, and so on, which are in the upper right corner. So if you have questions maybe on the talk, you can refer to the numbers if you like. Okay, so mu-pn is, as usual, the group scheme of nth roots of unity. Ah, okay, now I see it. This guy has come here. Okay. Yeah, sorry. And so we wanted to understand such models over very ramified DVRs. When the DVR ramifies more and more, there are more models, and this is very difficult to understand all of these models. And to do so, well, of course, it's natural to embed mu-pn inside the multiplicative group GM. But now this is actually easy to understand these models because all of them are suitable kernels like this. So the models calligraphic G, they appear as kernels in such exact sequences. Namely, anytime you take a closed subscheme like this inside spec R, so R is the given discrete valuation ring, and pi is a uniformizer. So now if I is the closed immersion, then you have a reduction map here. So you reduce mod pi to the n the local sections of GM. And if you view this as a sequence on the small flat site of the base ring, then this turns out to be surjective, and the kernel G is a smooth one-dimensional group scheme, which is a model of GM, and all of them are obtained in this way. So it's easy to understand models of GM. The interesting point is that this creates some group schemes over the truncated DVR, R mod pi to the n, which is, of course, an Artinian local ring. I mean, anytime you use this exact sequence and you take homology and so on, then the fact that the sheaf on the right is supported on the closed Artinian DVR creates many such group schemes. So this is one motivation, and another motivation, which is closer to the talk of today, is, well, just understand unipotent group schemes over Artinian rings, given that when you have models calligraphic G like on the previous board, there are special fibers. They are actually unipotent. So we wanted to understand these things. Now we started with the easiest Artinian ring, which is the ring of dual numbers K epsilon, where epsilon squared is 0. And so from now on, this is the Artinian base ring that I'm considering. Okay, now it is known that you can describe groups which are deformations to the dual numbers using cohomology. So namely, if you start from a group like this over K epsilon with a given special fiber, Roman G, then they are classified by cohomology group, which is H2 Bg with coefficients in what is called the Lie complex. So Bg here is the classifying stack. And this Lg Chech is the dual of the co-Lie complex. So this is the Lie complex. And it is known by deformation theory as worked out by Illusi, for example, that this is in bijection with the set of deformations of Roman G up to isomorphism. Now, in the case where the groups are actually smooth, the Lie complex is somehow simpler. It has an augmentation which makes it isomorphic to just the Lie algebra. So this becomes, in this case, so this is if J is smooth. The Lie complex is simply the Lie algebra, and this cohomology turns out to be just the cohomology of the group with values in the Lie algebra. So here it's understood that on the left-hand side, this is coherent cohomology, and on the right-hand side, this is group cohomology, but it's known that the coherent cohomology of the classifying stack is equal to group cohomology of the group. So this is standard. Now, this group cohomology group is also very well known to be classifying extensions, right? So this is isomorphic. This is in bijection with the set of extensions of G by its Lie algebra, where, so I forgot to say that here the Lie algebra is actually acted on by G, and it's the adjoint representation. So here again, modulo isomorphism. So, well, these two groups are, I mean, these two interpretations are known, but we wanted to understand directly the bijection that results here. And this is what I'll do today. And actually, I will present a geometric construction of this equivalence, and also I will categorify it. So we will categorify this bijection. Namely, I will turn this into an equivalence of the categories that are obtained when you remove the isomorphism signs.
So, sorry, okay. Can you be a bit more precise about what you mean by extension?
Yes, I'll do it right now. Maybe I can answer your question.
Okay, now it will come later. Okay.
Yeah, it will come later. I mean, so an extension is just yeah. I can do it here on this. So it's an extension is just a short exact sequence like this, right? Where E is a K group scheme, and the map from E to G is FPPF, say, so it's faithfully flat. So it makes E a Lie torsor over G, and well, since Lie G is commutative, there's the conjugation action of E factors through an action of G on Lie, which is the adjoint representation. Okay, I'll say it in more detail in a couple of boards. So here's an example to say, well, actually, what is the kind of group schemes that we are looking at? If you start from the additive group over the field K, then since this is smooth, the deformations of this have an underlying scheme which is necessarily trivial because it's deformations of an affine smooth scheme. So the underlying scheme, so this, of course, as a scheme is A1, and all deformations as a scheme are isomorphic to A1 over the dual numbers. And here are examples of deformations of the product law. The first is, so mod epsilon, this is supposed to be the additive group, right? And then here are two examples. The first one, you add this term epsilon x1, x2 to the p to the I. If I is at least 1, this is an example of a non-commutative group scheme, which deforms the additive group. And the second example is with the Witt cocycle, x1 to the p plus x2 to the p minus x1 plus x2 to the p over p. And this interpreted on the side of extensions, which I'm going to do in the main theorem, is going to be to give the Witt, the group of length 2 Witt vectors. This calligraphic G as a deformation of GA will be given by an extension which will be W2. Okay, so now I proceed to give the statements of the theorems I want to present. So here K is a commutative ring. It turns out to be useless to restrict to a field. It's actually not necessary. And then I introduce this notation for the two natural maps. So the spectrum of K epsilon has a structure map to K, which I call H, and spec K is inserted as a closed subscheme via the map I. And then the two categories which are relevant are, so the category GR over K epsilon. So it's the category of smooth affine group schemes over K epsilon. And the category of extensions. So as I said, smooth affine, so G is a smooth affine K group scheme. Lie G is its adjoint representation, and here this map is actually smooth, of course. So I can write it. Okay, so these are the two categories, and then I define the functor, the easy functor, say. So anytime you take a group scheme over K epsilon, that is an object of the first category, you can define its Weil restriction along H as follows. So it's given on, you can define it as a functor. So on the points with values in some K scheme, or you can pick a K algebra and restrict to K algebras, doesn't matter. This is the points of G with values in the base change of S to K epsilon, which is another notation for H upper star S, the base change of S along S. So if you look at this, actually, if you phrase G of S in terms of home SG using the Yoneda lemma, this tells you that actually H lower star is, by its definition, the right adjoint to H upper star, the pullback functor. Okay, so now here's the main statement. Item 1 says that this functor Weil restriction induces an equivalence of categories between the category of group schemes over K epsilon, smooth and affine, and the category of extensions. So this requires some work. I mean, it requires some work to see that this actually makes sense. Namely, it's not clear that the Weil restriction, as I just defined it, is an extension. So I'll explain this to you. And this isomorphism, this equivalence of categories, you can see over the category of K group schemes, namely to any group scheme over K epsilon, you can attach its special fiber, and to any extension, as before, you can attach the group scheme G that lives on the bottom of on the right of the extension. And then the second item of the theorem says that if you fix G, so this now is fixed, this Roman G, then you can view this equivalence as an isomorphism of Picard stacks. Let me recall briefly what is a Picard stack. A Picard stack is a little bit like a commutative group, But while a commutative group is a set, as an underlying set, a Picard stack is a category. Oh, well, the word stack here is not so important. You can think about Picard category. So it's a category endowed also with an internal group operation, and the names comes from the example of the category of line bundles, for example, on a variety, right? If you take a variety or a scheme, then it has a Picard group, which is the group of line bundles up to isomorphism. But if you don't think up to isomorphism, if you keep all isomorphisms, then you have the category of line bundles, and it has an internal operation, which is the tensor product of line bundles. And the fact is that, let me write on the bottom of the board, where if you, for example, if you want to check associativity of the tensor product, then this holds, but it holds only up to this is how it goes, right? And it holds only up to canonical isomorphism. Now, if you plug these canonical isomorphisms into the structure, what you get is called a Picard category, right? So it's a category endowed with a group operation. So so let me just tell you what are the internal laws of these Picard categories. In the category of groups over K epsilon, the addition operation is the sum, what is called the sum of deformations, which is familiar to people doing deformation theory. And well, let me not recall what this is precisely. But if you have two deformations of this Roman G, you can add them in some way by inserting K epsilon diagonally inside K epsilon 1 epsilon 2 somehow. And so that's for the left-hand category. And for the right-hand category, well, these are extensions, and there is the usual bare sum of extensions, which I guess also is known to people familiar with group cohomology and classification of extensions. So that is the statement of this theorem, which is the main statement I want to explain today. And then there's an application to unipotent groups. So in the next two slides, I'll take the freedom to be a little less interactive. So these two slides are prepared. And because this is mainly definitions, I want to give you the statement of the application to unipotent groups, but I won't devote much time to it afterwards. So, well, so in this application, K is going to be a perfect field. And let me recall that to any unipotent group scheme over K, there is attached a Dieudonné module, which is the object mu defined as follows. So it's the inductive limit, the union somehow of the homomorphism groups of U into Wn. Wn here is the group of Witt vectors of length n. And this module is actually a left D module because the ring D is acting on Wn, and the ring D is so-called Dieudonné ring, which is a WK algebra, where WK is the ring of Witt vectors. And then it's a polynomial ring generated by two indeterminates f and v. F stands for Frobenius and v for Verschiebung, modulo the usual relations. I put usual in quotes to be respectful for the people that don't know these relations. But let me give an example. For example, if you look at the group, the additive group GA, then its Dieudonné module is simply KF, which is the Dieudonné module where P is acting as 0 and V is acting as 0, which are not surprising relations if you know the additive group, namely the endomorphisms of GA given by multiplication by P and by Verschiebung, they are actually 0 on the group. So this is reflected in the Dieudonné module. Okay, now very briefly, I introduced this notion of admissible filtration, which is just what you obtain when you transport by the Dieudonné equivalence of categories the extensions that we had in the previous theorem. So this this Dieudonné equivalence is contravariant. So the extensions are upside down somehow. In other words, you should look at the quotient k of f to the d as the equivalent of the Lie algebra. Okay, so now this notion of filtration of finite type D modules is such an exact sequence, M1, M2. M1 is somehow reminiscent of the G, and M2 is reminiscent of the E in the extensions, where there are conditions on these modules Mi for them to correspond to unipotent groups, namely both Mi are erasable, which means that each of their elements is killed by some power of Verschiebung. This is the first condition. And the second condition is that they should be smooth, because I want to classify smooth group schemes. And this translates into the fact that Frobenius is a monomorphism.
By the way,
Okay.
sorry, are you thinking about commutative groups here?
Right, absolutely right. Unipotent commutative. Thank you. Absolutely right. I did not forget the adjective in the statement on the next slide, but here I did. Right, and now also I wanted to point out that after you define the notion for a Dieudonné module to be smooth, then you can define its Lie algebra and its dimension, and the D that appears here is required to be equal to the dimension of the Dieudonné module M1, because this is supposed to be the Lie algebra. Okay, now when you have this, you get the following theorem. So the functor that to any unipotent group over K epsilon, so U, this curly U is over K epsilon, then to any such U, it has a special fiber UK and a Weil extension, Weil restriction, sorry. And you can see easily that there's such a filtration of Dieudonné modules, and this sets up an equivalence between the category of commutative unipotent smooth group schemes over K epsilon and these admissible filtrations. Okay, so this is there's not much more than just the previous theorem together with the usual Dieudonné theory, as you can find in de Mazur and Gabriel's book. Okay. So let me proceed. So now I'm focusing on theorem 1. And I want to give a flavor of the equivalence. Okay, so first I go more into the structure of this Weil restriction. Starting from this curly G over K epsilon, here I recall the notations for H and I. Then, since the Weil restriction is defined as an adjunction, as an adjoint, then there is a canonical co-unit map of the adjunction, which I write beta or beta G, maybe like this, which morally is, well, here on the left-hand side, you see the epsilon as a formal variable. And here you evaluate. In the coefficient rings, right? This is a functor between this is map between functors defined over K epsilon algebras. So you evaluate on rings that are K epsilon algebras, and you can also evaluate epsilon in the ring that you are looking at. So that's the map beta. Okay. Right. And so the first observation somehow is this lemma that actually the kernel of, yes, question? The kernel of this map beta, which is a K epsilon group scheme, which I denote LG, I claim that this is a deformation of the adjoint representation of the special fiber. So the adjoint representation, Li of the special fiber G. Well, let me give you all the various notations that I've been using for the special fiber. They're all the same, right? Okay, so this you can check. It's actually not so easy. So the various lemmas that I will give you, none of them is trivial and all require some effort. Okay, now
Sorry, is G smooth or not in this lemma?
no,
No importance. Okay.
no, not for now. It's going to be in lemma 3, but before that it's not. So this is why I just wrote affine, which I think is, yes, this is important, but smooth is not required. Yeah. Also in the next lemma, so the next lemma is going to be useful later on, but this is now the good time to state it. Now I revert to a group scheme over the base field K, which is actually a base ring, because as I said, the fact that it's a field is actually not important. And so in our later constructions, we shall use this exponential mapping, which is the composition here. Or let me describe this. So here I introduce TG, the tangent bundle of G, which if you look straight at the definitions, you can view as H lower star H upper star G. This is the same thing as home spec K epsilon G. So it's a familiar expression maybe for the tangent bundle. And inside the tangent bundle, you have the Lie algebra. Now I pull this back to K epsilon by applying H upper star. And then this H upper star TG turns out to be H upper star, H lower star, H upper star G. And so there is this adjunction map beta for the group here, which is the pullback of G. And this goes to H upper star G. So this exponential is a morphism between group schemes over K epsilon. Morally, this is, well, you take a tangent vector and you map it to 1 plus epsilon x. That's what it is, right? So of course, if you want to do this, you need to have epsilon in your hands, and this you have when you pull back to K epsilon. So you must really base change in order for this exponential to be well defined. Okay, and so now my second lemma, again, with no smoothness assumption, is the following. So it applies only to those K epsilon group schemes that come from K. So in other words, this is a trivial deformation. Then under the familiar description of the tangent bundle as a semi-direct product, then in this case, we have the following description of LG, our kernel beta. This is simply the functor of pairs. Sorry. So H is in H upper star Li G, and G is in H upper star G, such that G is just the exponential of minus x. Okay, so this LG is, I recall that this is the kernel of beta, so this lives inside H upper star. So let me go one slide back, and so this lives inside H upper star, H lower star G. So this is really a K epsilon group, and that's how it can be described using the exponential. Okay, so this is actually going to be useful later. So you'll see this coming up again, but that was the good time to give it because we have the notations. Okay, so now let me come back to K epsilon group scheme, and now I assume that this is smooth, and then I claim that this sequence is exact. Well, LG was defined to be the kernel, so the main statement is that beta is actually a smooth map, and it's enough to prove that this is flat, faithfully flat. Well, that's the main content. So now, once you prove this, so this is a sequence of K epsilon group schemes, and if you restrict to the special fiber, this curly G would be a K group scheme, and this LG, as we said in lemma 1, this LG is a deformation of the adjoint representation, which means its special fiber is going to be Li G, and then we'll really get an extension as in the category X over K. So that will describe the functor in full. So here I take a couple of minutes to give an explanation on this lemma. So call Romagny the special fiber again, and let me write pi for the special fiber of beta, which is map from H upper star G to G, right? Notice that I upper star H upper star is the identity because I is a section to H. So you have this. Okay, now here comes the assumption that G is smooth, and this implies that all its deformations as schemes are trivial. And so this implies that, well, let me just write what it means. It means that there's an isomorphism of K epsilon schemes from the trivial deformation to G, extending the identity. And now you have a map from H upper star G to curly G, and you can use a junction to view this as or to infer a map from G to H lower star G. And if you look at the condition that the sigma was extending the identity, what you find is that this map here, this new map, is a section of the map pi. So of course, scheme theoretic section. Scheme theoretic. But it's enough to obtain that pi is surjective, and of course a surjective map of group schemes is automatically flat. Pi is faithfully flat. And then also beta, maybe by the fiber-West criterion for flatness, platitude par fibre, right? So pi is the special fiber of beta, and we have an Artinian ring, so it's enough to look at what happens mod epsilon. Okay, so that's where the smoothness assumption comes in, and then we have defined our functor. Let me just illustrate by an example, which is actually a counter example. An example where the lemma does not hold. So this is given by this group scheme G, which is finite flat but not smooth. So I define G to be the kernel of this endomorphism of GA. So this GA is over K epsilon. And the endomorphism is x to the p minus epsilon x. Okay, so this kernel is a finite flat group scheme. And you can check easily that the H upper star H lower star G is none other than GA itself. by the map that I indicated. A plus epsilon b goes to b. You just have to plug in a plus epsilon b into the expression of x to the p minus epsilon x and see what comes out. And then the sequence of the lemma, of lemma 3, is this sequence. This map beta here is the map from GA, which is the one we just computed, to G, which on points maps B to epsilon B. And then its kernel is the kernel of epsilon, which is certainly not flat. And this beta is not an epimorphism of flat scheme or flat sheaves or whatever. So, well, this is what happens in the situation that is not favorable. Okay, so that's the Weil restriction. And now I want to sketch the construction of the inverse functor. So for this, I start from an extension. So this is an object of the category x over k. Here, there's I write pi for the quotient map and I for the inclusion, which is a slight conflict of notation, but I think it should be okay. Now, the first observation is that Li G as a sheaf over G is actually a quasi-coherent module because it's a vector bundle. And since G is affine, the cohomology of quasi-coherent modules vanishes. So there's no H1. And so this E to G, which is a Li G torsor, it has to be trivial. In other words, it has a section. And that's all we need in order to describe extensions in terms of cocycles. So once we have this, for any chosen section S, we can introduce the cocycle C by the usual formula. C G G prime is SG, SG prime, SG G prime inverse. This is a 2 cocycle, and it allows to describe E as the extension, which I call, let's say, EC, which is, as a scheme, the product, and with the group law that probably most of you know. So this is the group law that is twisted by the cocycle. So this, for any cocycle C, this defines a structure of group on this product. And, well, by the constructions, this is an isomorphism with E. This map that takes X, G to, I guess, IX, S, G. Right, okay. So let me call tau S this isomorphism, which is defined by the choice of a section S. Okay, now the main statement is the following statement. So once I choose an S, there is this, first I focus on the extension EC, which was on the left hand of the isomorphism. And inside EC, you can define KC, which is the set of pairs xg, such that g is the exponential of minus x. This is where our lemma 2 shows up again. This is where lemma 2 hints the correct construction for this group. Okay, so now KC is, let me go one slide back. KC is a subfunctor of EC, and then I transport it by this isomorphism tau into a subfunctor of E, sorry. So K is inside H upper star E. Okay, then we have the following 3 properties. The first one is that K does not depend on the choice of S. The second property is that this is actually not just a subfunctor, but it's a closed normal subgroup scheme. and thirdly, this is functorial in E. Okay. And there the proof is, well, computations, which I mean, I would say they are a bit unpleasant. The enlightening part is the use of the operation of the exponential. But I must say that we were a bit surprised by how much complicated. I mean, it's much longer than we expected. I mean, we expected to prove these things quite easily, and actually it's not. Well, this is maybe irrelevant for you, but okay, so this is the main statement. And once we have this, we can introduce our quasi-inverse functor, which I call h dot e, and this is simply the quotient of the pullback of E by this group K. And this is what I call the Weil extension of E. For lack of better term, I don't think the term Weil extension was used before. It seems natural because this is the inverse procedure to Weil restriction. And the statement is that this gives a quasi-inverse functor to Weil restriction. H lower star. And what is more, this okay, yeah. So this again is needs to be verified, and one checks also that both functors respect the addition law that I described, namely the sum of deformations on the left of the equivalence and the sum of extensions on the right. Okay. Okay, so now I want to finish with some speculations on what's next. And for this, I recall the beginning of the talk. We were actually interested in studying finite flat group schemes, namely models of mu Pn. And we were also interested in Artinian rings like R mod pi to the n, a baby case of which could be, for example, W2K. And so it would be ideal to have a similar description of group schemes in this setting. So now the 2 points raise difficulties. The first situation of finite flat group schemes raises the problem that the Lie algebra is not the correct object. Namely, for smooth group schemes, it captures much of the differential properties of the group, but for finite flat group schemes is not the case anymore. And the correct object is the Lie complex. So this LG, which is the one I introduced when I mentioned the deformation theory result by Illusi. And the fact is that, well, this Lie complex describes correctly in finite flat group schemes. So this is good. But if we wanted it to replace Lie G, then we should cook up an equivalent of the notion of extension. We had extensions of G by Lie G, and this LG Czech is not quite a geometric object. But the good thing is that it's known to be a complex supported in degrees -1 and 0. For example, let me write an example here. If G is commutative, it is known by a theorem of Raynaud that any finite flat commutative group scheme can be embedded as the kernel of an isogeny of abelian schemes like this, and this allows to describe LG dual as the two-term complex omega 1 B, omega 1, yeah, B over R or over S, whatever the base is, to omega 1 A over R. So you have such an isomorphism. Yeah. So this is a concrete description of this this Lie complex. And there's a theorem of Deligne that you find in SGA4, which to each such two-term complex attaches an algebraic stack. So this is in SGA4. I don't quite recall which expose this is, but to the two-term complex that we had before, you can attach a vector bundle stack, which is this TG, which, if you know algebraic stacks and the quotient operation, you can define to be this quotient stack. So this does not depend on the presentation of the Lie complex. Now, the good thing is that although this is not a scheme anymore, but an algebraic stack, still it's a geometric object. I mean, people know nowadays how to do geometric with algebraic stacks. And this tangent stack could possibly fit into a three-term sequence, which would be the equivalent of the extensions that we had before. And the kernel of this TG deserves to be called the stacky Lie algebra of G. Okay, so that's for point 1. Now for point 2, I think it should be doable to proceed to. So let me recall. Point 2 is about Artinian rings. So I think it should be doable to proceed to the equivalence of categories for group schemes. I mean, in order to describe group schemes over, for example, W2K or more complicated truncations of DVRs by using the Greenberg functor in place of the Weil restriction. This is what the Greenberg functor is designed for. This is very much used in, for example, motivic integration theory. And I think it's so what you, of course, what probably the Lie algebra would be replaced by some by a different representation of the group G, but I think it should work. For example, there's work of Alexander Stasinski that described the green functor of W2K group schemes. The focus in his work was not so much in describing an equivalence of categories like we did, but rather in describing the internal group theory of the Greenberg functor in terms of, for example, what are the tori inside the Greenberg functor. It turns out so if I recall correctly, the torus of G would give a Cartan subgroup of the Greenberg functor, something like this, right? Okay. Yeah, so I think this is how it should work. Now, to finish, maybe I should give you an explanation why this is not done, actually, 1 and 2. This just because, as I said, we encountered more complicated computations than we expected when we worked this out. And now, since then, we started to do different things. And for the moment, we haven't worked this out. But I don't have much doubt that this is going to work correctly. Okay. I think, yeah, this is all I planned to say. I realize it's a bit short, but I'm open to questions, of course. In particular, I could give details on some parts. Yeah, thank you for your attention.
Okay. Okay, so for questions or comments, please be free to open the microphone and also to use the chat.
Is it possible that this might say something about Conrad's question about whether every like smooth group scheme over the dual numbers is embedded in GLN?
We looked at it. Yes, I looked at it. At some point, yeah, in the beginning, well, it turns out we developed this the whole business without any intended application to this conjecture. But of course, we soon realized that it was related. And then I tried. So what you obtain when you do this is basically if you start from so if you think you can, so you start from let me take the board. That's what it's used for, right? Okay. So you start from G. Oh, maybe so use. Let me rephrase the question for the people that don't know it. Use this to prove that any G over K epsilon embeds in GLN. This is your question, right? Then
yeah, I mean, one might throw in assumptions like smooth or affine or whatever, but sure.
Yeah, you can add some if you like. Yeah. No, okay, yeah. So probably smooth is not helpful. We don't expect. I don't know. At least affine, and of course finite type, right? And maybe smooth. Yeah, let us assume smooth. Then our theorem reduces to embedding the special fiber G inside some tangent bundle, some TH. Sorry, some TGLN. And this I don't know how to handle. So it seemed to me the question is essentially the same. Now maybe you have some ideas to embed G inside the tangent bundle of some GLN, which is, of course, well, the matrices, semi-direct product GLN. I don't know.
So Matthieu, K is a field here, right?
Yeah, sure. Yeah, yes. Yeah, for the moment, I don't know. I don't know, but it may be. I mean, the picture is very different. I mean, when you think about group schemes over K epsilon in terms of such extensions, the intuition is very different. So it might be that someone smart among the audience finds his way through this question. So yeah, but I haven't been able to make it. I've been discussing this a little bit with Brian Conrad also, but
is this reduction non-trivial? Is it difficult to embed the semi-direct product in another GLN for bigger N?
this one like this?
Yeah.
So I'm not sure I understand the question. Do you mean we could try to simultaneously embed G inside some GLN with big N by cooking the GLN in such a way that there is this semi-direct product in it, or?
No, I'm just asking about the reduction that you did.
Sorry. Oh, the reduction here is just using the theorem. So if you assume, okay, so if you assume that G is embedded inside GLN, then by using the equivalence of the theorem, the G is equivalent to some extension E, and the GLN is, so the extension that is attached to GLN is TGLN. So that's the equivalence. So the G that I have here is actually E right? So you apply, so so if you think about your given curly G as an extension E, and you know how to embed E inside TGLN compatibly with the extension structure, then you are done. So E, right, if you can embed like this. So of course you can start from an embedding of G of the special fiber G inside GLN. Right? But then you must, okay, so maybe, okay. And this, the part that requires an argument is the yellow arrows. This I don't know how to do. Well, I must say,
Other questions?
Yeah.
Yes.
I thought, yeah. Other questions?
No.
What were you saying?
Yes, please, Bert.
Oh, sorry, I meant to ask Matthieu, you started to say something.
Okay, so I think he wants to discuss with you separately. I mean, but why not? I mean, this is okay. So thank you very much for attention, and we have a talk once again in 1 week. So thanks again, Matthieu, and see you next week.
Thanks
Bye.
to everyone. Sorry for being a bit short. I should plan
No problem. No
more
problem.
detail next time.
Nobody has ever complained about that.
Thank you. So last time I lectured on this was a little bit more than 1 year ago, and I was too long.
No, but this is because you already prepared things. You were a bit scared
Right. That's right.
of being long, but
yeah, I
And this was good.
yeah, yes, and
not too fast.
this question at the end is very interesting. I mean, this is I mean, it shows exactly. I mean, how. I mean, the limit of our knowledge. This is.
Yeah. I must say that I've been thinking about this embedding question for not more than a week or 10 days. And yeah, it may well be that there's a way to go further, to lift. So you embed G in GLN, and then you want